we're still answering the chemistry exam paper, and like I said, useful to everybody who is interested in seeing how questions in first year come in chemistry. So we'll pick it up from where we ended, that is question 5 and question 6. So for question 5, we are told the vapor pressure of a substance is 21 millimeters of mercury at 200 Kelvin. Calculate the vapor pressure at 310 Kelvin if the enthalpy of vaporization is that. So let's take note of piece of the data that we have. So we have the pressure being equal to 21 millimeters of mercury, and then the temperature being 200 Kelvin. Then we are asked now to calculate the vapor pressure again. This is like the second case where we are told the temperature, we call it T2, is equal to 310 Kelvin. So I want us to find the second value of pressure. Now we are told the enthalpy of vaporization is 12 kilojoules per mole. So basically, looking at this piece of information, if you've done phase equilibrium, you'd understand that basically, if you've done equilibrium, you would actually have heard of Closures-Caperion equation. Okay, so that's the equation that we'll actually use here, Closures-Caperion equation. Okay, if you're on our site, just go to our topic solutions and their properties. You'll be able to find this. Okay, so the equation is very simple, kind of related to the Linus equation, except it deals with pressure instead of the K values. So P1 over P2, and instead of having the energy, the activation energy, we put the enthalpy of vaporization in this formula. So at that particular point where we have negative EA, we have that. Everything else is basically the same. 1 over T2 minus 1 over T1. And so we just have to just plug it into this equation. Okay. So P1 over P2, our P1 is 21. Okay. So I'm sure we still want to work with what the units we've been given. So 21 over our P2 is what we don't know, as we're trying to find. And then for our enthalpy of vaporization at that particular point, the kilo that you're seeing represents 1,000, so just put 12,000. So that will do with joules per mole. And then for our rate is supposed to be based on the units of the temperature that we're using. For the temperature that we're using, the units are in Kelvin, so we use 8.3148. Okay. It's also in joules, so units are actually matching up. Let me just indicate the value I'm using, 8.3148. Actually 5, not 8. 45 joules more negative, okay, negative. That's why even for the enthalpy of vaporization, I decided to use 12,000, so the units will become now joules per mole. So matching up, right? Okay. Temperature is in Kelvin. So T2 is 310, and then T1 is 200 Kelvin. So now the work that just lies now up is just for you to simplify this, right? That's all. So let's simplify. I'll maintain the left. Natural log of 21 millimeters of mercury over P2 is equivalent to, so 12,000 divided by 8.314. Okay, so 1,403.26. The units that would remain after we've cancelled this and that, the joule and the joule, will just be that K negative, and then 1 over 310 minus 1 over 200. Remember, we are subtracting. We're subtracting there. No, we're not subtracting, we're multiplying here. Okay. So 1 over 310 minus 1 over 200. Let me do that. 1 over 310 what's wrong with my page? 1 over 310 minus 1 over 200. So I'm getting a negative 1.7742 times 10 to the power negative 3 k negative, right? Okay, so multiply the two now. We maintain what's on the left. So the negative 1.7742 times 10 to the power negative 3 multiplied by this first part. By the way, this is supposed to be a k positive when it comes to top. Okay, so that's negative 2.561. Okay, with no units at this particular point. Okay, not forgetting that our pressure 21 is having milliliters per mercury. So natural log is a log with a base E, right? So using the laws of bases, we can just actually move the base to the other side. So that we've got E negative 2.561 becomes the power on the right hand side. So we've applied logs to help us simplify this. And so this is in mercury, millimeters of mercury. And so our pressure 2 is basically your E raised to the power negative 2.561 divided by 21. Okay. So grab your calculator and then punch E on the calculator, put negative 2.561 divided by 20. Whoa, what have I done in my calculations here? Is this how it's supposed to come out? We have natural log of 21 over P2 is equal to negative 2.561. We have 21 over P2 is equal to E raised to the power negative 2.561. And so if you make P2 the subject of the formula, you cross and multiply, you end up with P2 multiplied by E raised to the power negative 2.561 being equivalent to a 21. Yeah, that's correct now. So our P2 is supposed to be 21 millimeters of mercury divided by E raised to the power negative 2.561. Okay, yeah, that's now fine. So 21 divided by, open brackets, E raised to that power. Okay, so that's basically equal to 271.9 millimeters of mercury, which I can round off to the question had every figure in 3 significant figures. I would end up with the same 272 millimeters of mercury. So that's the pressure. That's the second pressure that would have. Actually, this is not the question we're answering. The question we're answering is the one on top. Okay. So what can you actually notice here? So the vapor pressure is 272. So after increasing the temperature, even the vapor pressure has also increased. Okay, makes sense. Okay, so don't forget we're answering. So if we go back to our A6, a flask contains a mixture of 1.24 moles of hydrogen gas. So we've got hydrogen gas and then with oxygen gas. So we've got 1.24 moles of hydrogen and 2.91 moles of oxygen. So if the total pressure is equal to 104 kilopascals, calculate the mole fraction and partial pressures for each gas. Okay, quite interesting, right? So mole fraction, partial pressure. So this is the total pressure. Let's add the total number of moles as well. 1.24 plus 2.91. So that is giving me 4.15. So that's the total number of moles. So to find the mole fraction, it's actually very simple. So the number of moles of that particular gas, hydrogen 1.24 divided by the total 4.15. Oxygen 2.91 divided by the total 4.15. So this one 0.299, there's 0.70. So these are like the mole fractions, no units. Okay. Now the mole fractions, of course, would help us to even answer the second part of the question, the partial pressure. So mole fraction for each multiplied by the total pressure, which was 104 kilopascals. Now the K represents 1,000, so 104,000 pascals equal to the other part 0.70 multiplied by 104,000. So the units are pascals, of course. So the partial pressures of each gas. For the first part, the hydrogen, that's giving me something like 1,200 pascals. If you want, you can divide by 1,000 so that it becomes in kilopascals. That would be 31.2 something kilopascals. For the other part, for oxygen, that's 72,800 pascals. So if you want to convert to kilopascals, you just divide by 1,000. That's how you handle question 6. Okay, so we're now on question 7. The decomposition of A to produce B and C is an exothermic reaction. Okay. What happens to the equation? So the key term there is exothermic. Exothermic is a reaction that produce, emit, or release energy. Okay. What happens to the equation when if A is increased, if the temperature is reduced, if the volume is reduced? So this is coming from the concept of Chatelier principle. Okay. What happens to a system in equilibrium, as you can actually tell by the symbol there? What happens to a system in equilibrium when you affect the concentration, the temperature, and the volume? Okay, so I've actually covered that comprehensively as well. If you want to know more about it, just go on our site. The link is in the description below this video. Okay, so answer it. A at equilibrium with B and C. Okay, so this is exo. So let's assume this reaction is at equilibrium. What would happen if we increase the concentration of A? Well, what does it mean when you say a system is in equilibrium? It implies the rate of the forward and the backward reaction is the same. Now, adding air would affect the equilibrium because there would be more of air than required. So air is supposed to be converted to B and C to balance up. So when you increase the concentration of the reactant, for the first part, the forward reaction is favored to produce more of B and C. Okay, that's for the first part. The opposite is true. If we reduce air, there would be less of air. So B and C would react to produce air. So it would be the backward reaction favored. So everything is just trying to counteract whatever you're trying to do. If you increase C or B, we have to form more of air. If you reduce B and C, we have to form more of it. So you get the idea. That's for N. For B, now the temperature is what is interested in this concept of exothermic reaction. So an exothermic reaction is a reaction that emits or releases energy. So think of it as energy being what? Being, let's call it enthalpy actually. Think of the enthalpy to be what? Think of it to be a product because it's emitted or lost. So it's a product. So now imagine you reduce the temperature. So I'm trying to just give you something that can help you think or find the answer faster if the temperature is reduced. So consider it in this case to be a product. So what happens if you reduce it? So there is need for us to form more of it, right? So what happens? So the forward reaction will be favored. Okay? If we are to increase the temperature of the reaction, that means we've got more than needed heat to release, right? So if you increase the temperature, there would be more of air forming in such a case, because air or backward reaction is going to be endothermic, so it would actually use that energy. That's a difference. I hope you get it. If you've not gotten it, you want to go to our site and go under chemical equilibrium, look for the Chatelier principle. Save your questions on the principle of temperature and other things like pressure. Now for volume, if a volume is reduced, now this is now where you look at the moles that we have. Here we've got the single mole for the reactants, so products we've got 1 mole plus 1 mole giving us 2 moles. So reducing the volume would favor the side with less moles. So if you have to reduce a volume, the reverse reaction, so it's going to favor the backward of the reverse reaction. Because we reduce the number of moles, the volume is reduced. So we form something that is smaller. And then of course the opposite is true. If we were to increase the volume, the reaction would favor the side with greater moles. Okay, I hope you've now gotten some ideas of the Chatelier principle in a simpler and interesting manner. Provide the IUPAC name for the molecule shown below. These are very simple concepts. Okay, so this is from organic chemistry. Organic chemistry is my favorite topic in chemistry, so you want to check it out as well on the site. I've covered some basic principles from the conversions of the skeletal structures into the Lewis structures and vice versa. Okay, and also things to do with IUPAC names. These are cyclo compounds, so we add the name cyclo for the parent structure. Now there's a double bond somewhere there, so we can actually call it cyclo alkene. Now how many carbons do we have? 1, 2, 3, 4, 5, 8 carbons in the ring. So since it's having a double bond somewhere, I'll call it octane. If it was just a single bond, it would have been octane. Now octane is the parent name for the cyclic compound. Now that's just the methyl. So we've got two of them. So call that dimethyl. Okay. So since we only have one there, we'll align it in a way that we give it the lowest possible position, right? Okay. How do we balance this now? So let's give ethene the lowest possible group, right? Position. So let's do this. 1. Let's say it's position 1. So count the other way around, counterclockwise, so that bond is closer as we count. So 1, that would make that to position 2, 3, 4, 5, 6, position 6. So on position 2 and 6, dimethyl. Actually, I prefer small letters for the prefixes. 2, 6, dimethyl, and then parent structure is cyclooctane. So the moment you see tin there, it implies in this case on position 1 or the chain or the compound, that's where we have that double bond existing. Okay, that's a simple name for the simple IUPAC name for that structure. There's a video over 1 hour just naming these similar compounds, so you want to check it out on our site as well, and the organic chemistry section. Okay, and so that's the end of section A. We'll now move to section B. Okay, in case you want to see some more questions we have. Okay, all these questions are answered in this video. Okay, so if you want to access it, just basically visit our site. You have it in full, or just paying for Patreon or YouTube Premium, you'll be able to access it. Okay, so that's it for section A.